Hello and welcome to this presentation. My name is João Henriques and today I'll be presenting the work titled The Identification of Orthotropic Elastic Properties of Fluid by Digital Image Correlation and Finite Element Model Updating Techniques, which the authors are me, José Xavier and Gil Andrade Campos. This presentation is divided in 5 main parts, beginning with an introduction to wood and wood-based products, while also giving an overview of the goals of this work. Then I'll be presenting the experimental tests performed, followed by the methodology used to analyze and process the experimental data in order to obtain the results. And finally, I'll be presenting the main conclusions. Wood and wood-based products have been gathering momentum over the past decades due to policies of sustainability and green economy. Wood is a complex biological material with an heterogeneous and hierarchical structure. A mechanical description has been proposed based on an isotropic behavior along with 3 orthotropic material directions, the longitudinal, radial, and tangential directions. The characterization of orthotropic material properties is crucial in computer-aided engineering systems in order to accurately reproduce the material behavior, fostering innovation with the development of new products and design of wood structures. In the figures, we can see 2 different perspectives of Metropole Parasol. This is the largest wooden structure in the world located in Seville, Spain. The experimental characterization poses several issues due to the inherent hierarchical, heterogeneous, and anisotropic modeling behavior of wood. Classical approaches involve identifying the material parameters from a series of classical mechanical tests that produce quasi-homogeneous strength fields using punctual measurements. However, as the number of experimental tests and material parameters grow, it becomes increasingly difficult to identify these in an exploratory manner. Novel optical methodologies like digital image correlation can provide full field measurements, and when coupled to inverse identification techniques, for instance the FAMU or VFM, they have the potential to reduce the number of experimental tests required to accurately identify the material properties. Work addresses the identification of linear elastic orthotropic constitutive parameters of pinus-pinaster height through digital image correlation and the finite element method updating, using a single uniaxial compression test under quasi-static loading conditions with on-axis rectangular specimens oriented on the radial tangential plane. Pinus-pinaster at a diameter at breast height of a single tree of approximately 60 years old was tested. Radial boards were initially cut and air-dried to a moisture content of about 12%. Clear wood specimens were then manufactured on the RT plane with nominal dimensions of 20 by 10 by 4 mm in the radial, tangential, and longitudinal directions respectively. Compression tests were carried out on an Instron microtester machine with a controlled crosshead displacement rate of 0.5 mm per minute, while the axial load was measured by a 2 kN load cell. A lubricant was also applied between the specimen and the compression platens to reduce the friction and avoid excessive barreling. Digital image correlation was coupled to the tests to evaluate the specimen deformation across the whole region of interest, integrating several annual growth rings. The optical system consisted of a Balmer optronic camera with an AF micro-Nicker lens. The speckle pattern was created by airbrush painting with an average speckle size of 2.7 pixels. The lighting system and the exposure time were set to avoid pixel saturation and ensure the best contrast of the speckle pattern, while loading and image recording were synchronized during the test at an acquisition rate of 1 Hz. The selection of the DIC setting parameters is a key topic when performing measurements through full field measurement techniques that influence the obtained results. This selection was carried out using the performance analysis module from MatchID software with a set of different parameter combinations in a total of 650 analyses. The figures summarize the convergence study performed comparing the strain component on the radial direction versus the virtual strain gauge size regarding 2 selected points, early wood on the left and late wood on the right. Using a larger VSG leads to a higher level of smoothing of the measurements, minimizing the inherent noise of the experimental data, but also leads to the loss of strain gradings that are expected in heterogeneous materials like wood. Therefore, a compromise must be found between spatial resolution and accuracy. Selection of the DIC setting was based on this compromise and is represented in the figures by a yellow dot, being chosen a point that gives good spatial resolution, which is particularly important in heterogeneous materials such as wood, and simultaneously good accuracy since they are within a convergence band of DIC settings, where the increase of the VSG does not have a significant impact on the signal measured. The CAD specimen geometries for the finite element model were developed based on the experimental images, and a finite element model was implemented using ANSYS mechanical APDL software using 2D 4-node structured solid elements, mainly quadrilateral, changing to triangular when it is required to fit the irregular geometry of the annual growth ring structure of wood. Regarding the boundary conditions implemented in the FEA model, we use DIC-based experimental boundary conditions on the left and right boundaries of the specimen, interpolated between the DIC and the FEA meshes, smoothed by a four-order polynomials function. The FEMU is used to identify the 4 orthotropic linear elastic parameters of wood. The idea behind this method is to iteratively update the unknown material parameter set by means of an optimization procedure in order to minimize a cost function. The objective cost function adopted in this study is described by the difference between the experimental and FEA results, including the load and strain fields, where T represents the unknown variable and WF is a weighting coefficient between the strain term, ETS, and force term, ETF. The strain term describes the difference between the experimental and numerical strain fields, normalized by the max value for each strain component, where the variable n represents the total number of full field measurement points. Similarly, the force term describes the difference between experimental and numerical loads, normalized by the experimental load measured by the load cell. A flowchart describing the material parameter identification chain using FEMU is presented in the figure. An initial set of parameters is given to the finite element model in order to start the iterative process of FEMU. The numerical results, which are interpolated from the FEA mesh to the DIC mesh in order to match numerical data locations and experimental data points, are required to make an evaluation of the cost function. The iterative process continues using an optimization method in order to generate the next set of material parameters until a minimum of the objective function is reached and the parameter set stagnate. The optimization method used is the Nelder-Mead simplex method, which is a simple direct search algorithm. Here, a simplex is generated beginning with as much vertices as the number of variables plus 1. Then, a sequence of transformations is made with the goal of minimizing the objective function value at its vertices. The initial set of material parameters are considered reference values, and the WF used is 10 power to the minus 3. The convergence study for all 4 material parameters identified throughout the identification method for all specimens is presented in the figures, with identified material parameters being the modulus of elasticity on the radial and tangential directions and the Poisson's ratio and shear modulus on the RT plane. The differences between experimental full field strain measurements and numerical results are minimized. The figures show the experimental DIC strain fields in comparison to the final calibrated numerical strain fields for one of the specimen under analysis, and the difference between these two strain fields normalized by the maximum value of strain for its corresponding component. As expected, in the difference fields, it is possible to observe the annual growth ring structure of wood, being a major component of this due to the numerical homogeneous modeling of wood used in this work. The presented table and bar chart describes the identified modulus of elasticity on the radial direction for each specimen, including the mean value, standard deviation, and coefficient of variation. The results show some dispersion for each specimen, which is expected due to the inherent natural variability of wood. However, the mean value for this identified parameter agree with reference values for this wood species. Similarly, the results for the modulus of elasticity on the tangential direction are presented here. The anisotropy ratio given by the ratio between the modulus of elasticity on the radial and tangential directions for the mean values is 2.08, which is concordant to the typical values reported in literature for this wood species. Proceeding to the results for the identification of the Poisson's ratio on the RT plane. The coefficient of variation in this parameter is low, being at 6.8%, while the mean value identified is within the proximity of the reference value. Finally, these are the results for the shear modulus identification on the RT plane. The values for this parameter seem to have a higher variation, with a coefficient of variation of 38.8%, which suggests that there is a dependency on the test configuration used and the identifiability of certain material parameters due to the lack of sufficiently heterogeneous strain fields. Presenting you the main conclusions of this work. The proposed methodology, based on a single uniaxial compression test to simultaneously identify 4 orthotropic elastic parameters, proved to be effective in identification of 2 of the 4 RT linear elastic constitutive parameters of Pinus pinaster, being the modulus of elasticity on the radial direction and the Poisson's ratio on the RT plane. Nevertheless, there is the potential to identify all material parameters with only one test configuration, given that the test configuration submits the material to a combined state of stress and strain in a way that all material parameters play a role in its mechanical behavior. In future work, other single test configurations can be inspected in order to enhance the identifiability of fluid material properties. Thank you for your attention.